Hi, this is Radha Nagarajan from Marvell. Today we'll present some of our work in extending the data center data rates from 400 gig to 800 gig and 1.6 terabit per second. Along the way, we'll discuss what post-more means to data center networks in this context. Let's look at the 2x speed scaling that is required from the networks of today. We have 400 gigabit per second networks today. That is either 16 QAM 1 lambda for networks or interconnects between data centers and 53 gigabaud PAM4 4 lambdas for interconnects within the data center. There are multiple ways in which we can achieve this 2x speed scaling. First is double the number of lambdas. Inside data centers, 8 lambda 800 gig to 8 lambda 1.6 terabits. And outside data center, 1 lambda 800 gig to 2 lambda 1.6 terabits. Both of these are under consideration. There are issues with power, size, cost, and the number of lambdas is not easily scalable. The next approach is to double the analog bandwidth. This would take us to 800 ZR per lambda or 200 gigabits per second per lambda. It's 2x the baud rate, and the challenge is the analog bandwidth. And of course, we can get into higher order modulation formats. To double the data rate, one has to go from PAM4 to PAM16 and 16 QAM to 256 QAM. The SNR requirements are fairly onerous, and the complexity in encoding and decoding these formats are equally daunting. And there are a number of engineered solutions. The trade-off between complexity and baud rate, 64 QAM, 90 gigabaud, or PAM6 90 gigabaud solutions have also been proposed. So if you were to look at the options that are out there, 2x the baud rate seemed to be the leading contender, and 2x followed by 2x lambdas. Actually, 8 lambda 800 gig is under development today, and the engineered solutions have been adopted for metropolitan and longer haul transmission systems. Let's look at the evolution of inside data center networks and the data rates. It's the evolution of PAM4 from 400 gig to 1.6 terabits per second. At 400 gig, it's 4 lambdas. At 4 lambdas, the line side is 100 gig PAM4. 800 gig at 8 lambdas, the number of lambdas has scaled, so it's 100 gig PAM4. And these three options that are variants on 800 gig and 1.6T are at 200 gig per lambda PAM4 on the line side. You also have to look out for the electrical lanes at the input. That is the capability of the modules. We have tried to keep them at 8 electrical lanes and with one option at 16. And this is currently only supported by OSFP XD. 8-lane versions might be possible with OSFP, QSFP-DD or OSFP. And OSFP-DD also supports 8 lanes. So whether it's 8 lanes or 16 lanes determines the host electrical interface speed from 50 gig to 100 gig. And eventually, if you want to get 8 lambda 1.6 terabit, the host needs to scale to 200 gig PAM4 as well. This shows the following show the trade-off on the DSP nodes. We believe eventually at 1.6 terabit per second, we'll have to get to a 3 nanometer node. And DSP die area, power, and optics, and the bandwidth. What we have to keep an eye on the bandwidth. Once we go to 200 gig per lambda, the optical bandwidth goes up. But you would see here the optical bandwidth didn't quite go up by a factor of 2. I'll get to that in a moment. The optical power consumption doubles easily when you go from 4 to 8 lambdas. And it's normalized to 1 at 400 gig. And the DSP power doesn't scale downwards as much as you would hope as we go to a smaller and smaller node, smaller and smaller nodes. What does post-Moore mean in this context? The smaller CMOS nodes do not lead to an increase in analog bandwidth, and neither do they reduce the analog power consumption substantially. So we still have to look at a number of other things to get us the bandwidth. One is improvements in the components, just increasing the bandwidth to as much as possible. And the second, which we have chosen to lump them, is compensation. As you can well see, this reflects an FFE-DFE type combination. Correction, which is the fault error correction. And last, we'll deal very briefly with integration, here again to reduce power and improve the analog bandwidth. Components. For 100 gigabaud TIA and drivers, these are under development at Marvell. They typically have bandwidths in excess of 60 gigahertz for the TIA and about nominally 70 gigahertz for the driver. One of the important things to notice is a relatively large amount of peaking, which also relates to the compensation part of it that we'll get to in a moment. And these drivers achieve about 3-volt swing. For 90 and 100 gigabaud, they have the best linearity. And these TIAs probably have the lowest noise at 90 and 100 gigabaud applications. Components. Silicon photonics. Silicon Mach-Zehnder modulators. For us, the third generation of silicon Mach-Zehnder modulators are under development. The first generation had bandwidth of the order of about 30 gigahertz. And the second generation bandwidths in order of half bandwidths in order of 50 gigahertz. The first generation components were deployed in 28 gigabaud, 100 gig PAM4 colors applications for inter-data center interconnects. And the second generation devices would be used in applications between 60 and 120 gigabaud, and for 4 to 800 gig data rates. For 16 QAM for inter-data center, or PAM4 for intra-data center applications. The Gen 3 devices under consideration, under development, these are all experimental data, by the way, are not ready for deployment in devices. The next component, again on the silicon photonics platform, integrated germanium photodetectors. Our generation 1 devices had a bandwidth in excess of 30 gigahertz, so it's more than enough for the 28 gigabaud, 100 gig PAM4 colors DCI applications. Our Gen 2 devices have bandwidths in excess of 60 gigahertz. These are the devices that would be used for between 60 gigabaud and 120 gigabaud, and between 400 gig and 800 gigabits per second applications. Again, 16 QAM for DCI and PAM4 for intra-data center applications. Now let's look at compensation. To understand compensation, you have to really look at the optical channel and the impairments. You have the transmit side and you have the receive side. On the transmit side, the limitations are analog bandwidth at the DSP and DAC, analog bandwidth and reflections at the receiver, the driver, analog bandwidth and level dependent RIN for PAM4 especially, for the laser and the modulator. And on the receive side, analog bandwidth and short noise for the PD-TIA combination. And on the ADC resolution and analog bandwidth. So what are the mitigation or the compensation that we can put in place? On the transmit side, for pre-equalization is essentially feed-forward equalization, FFE. And for the driver and TIA, analog peaking, as we saw on the previous slides. And also low noise, TIA design. And the magic happens in the DSP of the receiver. Feed-forward equalization, decision feedback equalization, maximum likelihood sequence detection, and forward error correction. And one of the things we have to remember, the baud rates at PAM4 for 200 gig per lambda is 113 gigabaud, and for 800ZR it's 120 gigabaud 16 QAM. Fiber chromatic dispersion, group velocity dispersion scales quadratically with baud rate. And that's something we need to address even for intra-data center links. Without going into a lot of detail, MLSD, maximum likelihood sequence detection, is one of the enhancements that we are proposing to actually mitigate the analog bandwidth needs at these baud rates. This is actually the analog bandwidth for the whole system. What MLSD allows you is enables a relaxation of the system bandwidth instead of doubling it from the 100 gigabit per lambda infrastructure. This particular modeling was done for 115 gigabaud PAM4 with an RX OMA, or receiver OMA of minus 4 dBm, RIN of minus 145 dB per hertz, extinction ratio of 5 dB, and equivalent of 16 picoamp per root hertz. So using a MLSD equalizer would allow us to design optical components which do not have a very strict analog bandwidth requirements. Next is correction. Advanced forward error correction codes. If you were to look at, there are a lot of codes published in literature today. This is a trade-off between NCG, which is net coding gain, net of the coding overhead, for a bit error rate of 10 to the minus 15, plotted against the overhead percentage, bound by two limits: the soft decision Shannon limit and the hard decision Shannon limit. So a lot of these codes have some level of soft decoding. And as you can well see, the most efficient coding schemes have between 5% and 15% overhead. We are trading off net coding gain of the FEC against power consumption of the ASIC implementation. It's important. And the net coding gain doesn't keep going up with overhead, because as your overhead increases, the penalty you pay for the overhead also increases. So there's a saturation point. So 5% to 15% is about the optimum. And if you were to look at the KP4 FEC that's available, that's used commonly inside data center, it's got a 7 dB net coding gain. We have two options. One is a SFEC and the SFEC 200. These are concatenated wrapper FECs, which would add 1.5 dB and 2.5 dB net coding gain to the basic KP4 fault error correction code. Latency. Correction code and complexity isn't the only factor we have to consider. KP4 is a standard IEEE FEC for inside data center. There's staircase FEC, which is the ITUT standard for 100 gig coherent links. And there's a concatenated Hamming in staircase FEC, which is the ITUT and OIF standards in 400 ZR links. These are the relative overheads between relatively 5 and 15%. The net coding gain goes from 6.9 dB for KP4 to 10.8 dB for the CFEC, concatenated FEC. And these are relative FEC thresholds. As you can see, the power scales, not surprisingly, and the latency goes up. Latency for a KP FEC is well under 100 nanoseconds. And for something like a staircase FEC and a concatenated FEC is the order of 1 to 4 microseconds. So there's a 2 order of magnitude difference in latency between the two, and that matters a lot for inside data center latency sensitive applications. And integration. If you were to use silicon photonics as a platform, and if you were to integrate, co-design the drivers and TIA, integrate them directly on a silicon photonics chip. In this particular case, they have plated pads, UBM pads, and you have bumps, TIA and driver that are bumped. You would get something like this using silicon photonics as the interposer. And silicon photonics is a very versatile platform. We've actually demonstrated this a couple of years back, where you can have a TIA and a driver and fiber coupling, lasers, as well as single layer caps, all integrated onto a silicon photonics platform. This allows for lower power consumption, lower equalization between the driver and the modulator, reduced reflections, and overall higher bandwidth. In this talk, we have explored several technology options when you're up against the analog bandwidth limit at 800 gig and 1.6 terabits per second. Thank you.